What if the most destructive object in the universe, the very symbol of cosmic annihilation, is not an ending at all? What if it is instead the most profound beginning we have ever imagined? For generations we have seen them as the ultimate terminus, the universe's dead ends. We have called them monsters, singularities, points of infinite destruction, from which nothing, not even the radiant speed of light, can ever hope to escape. They are gravity's final tyrannical victory over matter energy and the very fabric of space-time itself. A region of the cosmos where the rules of existence as we understand them are not just bent, but shattered into incomprehensible fragments, crushed beneath a weight so absolute it defies all physical description. This is the black hole as we have always known it, a one-way door to oblivion, a silent, perfect predator, lurking in the interstellar darkness, waiting patiently to consume anything that strays too near its fatal shore. You have seen the images rendered from the complex mathematics of relativity of a sphere of perfect blackness set against the warped tapestry of starlight. This boundary, this precipice of the abyss, is the event horizon. It is a term that sounds deceptively gentle for what it truly represents, the most severe and unforgiving frontier in all of creation. Crossing it is not a journey, it is an erasure. The instant you pass that invisible demarcation, your fate is sealed. Your future timeline now points in only one direction, towards the infinitely dense, infinitely small singularity at its heart. The gravitational pull becomes so extreme that it overwhelms every other force in nature. Your body, your starship, the very atoms that constitute your being would be stretched into a stream of particles in a process gruesomely termed spaghettification. It is a place where time and space exchange their fundamental roles, where moving forward in time means moving inexorably toward the crushing centre. There is no turning back. There is no fighting it. There is only the fall. We see their handiwork across the cosmic expanse. We see stars giants 100 times the size of our own sun caught in a delicate doomed dance, orbiting their unseen executioners. We watch as these colossal spheres of plasma are slowly unravelled, their gaseous outer layers siphoned away in a luminous spiralling accretion disk. This disk, a celestial hurricane of superheated matter, glows with an impossible ferocity as friction and tidal forces raise its temperature to millions of degrees. It blazes brighter than 1,000 galaxies combined, a final brilliant scream of matter, being torn asunder before its final plunge into the quiet dark. This is the black hole's roar, a testament to its power, a beacon of its destructive appetite. At the heart of our own Milky Way, a supermassive leviathan named Sagittarius A holds our galaxy together. In its gravitational grip, a silent monarch reigning over a kingdom of 100 billion stars. It is a cosmic anchor, but it is also a slumbering beast. Its very presence shapes our galactic home, a constant humbling reminder of the power that lies dormant in the deep. This vision of the black hole as the ultimate consumer is not wrong. It is simply incomplete. It is a single, terrifying chapter in a much larger, more bewildering story. To uncover the next part of this epic, we must stop thinking of a black hole as merely a passive object defined by its mass alone. We must introduce a new transformative property, a characteristic that changes it from a mere cosmic drain into a dynamic, churning celestial engine of almost limitless power. That property is rotation. Most things in the universe spin. Planets spin on their axes. Stars spin a legacy of the collapsing clouds of gas and dust from which they were born. Galaxies themselves pirouette in a grand slow-motion ballet that takes hundreds of millions of years to complete. And so too do black holes. When a massive spinning star finally exhausts its nuclear fuel and collapses under its own colossal weight, it does not simply shed its angular momentum. That rotational energy, the ghost of the star's former life, is conserved. It is inherited by the black hole it becomes. Suddenly our picture changes dramatically. The monster is no longer sleeping. It is awake, and it is spinning in some cases at nearly the speed of light. This is not a simple rotation like a ball spinning on the floor. This is an object with the mass of millions or even billions of suns compressed into a space smaller than our solar system, rotating at a truly unimaginable velocity. And with that spin, it does something extraordinary, something that Einstein's theories predicted, but that even he found difficult to comprehend. It does not just warp the space and time around it, it actively drags the very fabric of the cosmos along with it. Imagine dipping a spinning spoon into a jar of thick honey. The honey closest to the spoon is forced to swirl with it, creating a whirlpool. The farther away you get, the less the effect is felt until the honey remains still. Now replace the spoon with a spinning black hole, and the honey with the four-dimensional canvas of spacetime itself. This is the phenomenon of frame dragging, or the lens-thirring effect, a cosmic whirlpool of staggering proportions. Spacetime is no longer a passive stage upon which events unfold. It has become an active, violent participant, a rushing river of distorted reality. This titanic vortex of spacetime gives rise to a truly bizarre and counterintuitive region, a place that exists outside the event horizon, yet is utterly alien to our experience. It is a ghostly, invisible bubble of forced motion, a buffer zone between the relative sanity of the universe and the absolute madness of the black hole itself. This region is called the Ergosphere. The name comes from the Greek word ergon, meaning work, and for a very good reason. For within this maelstrom, work can be extracted. Energy can be harvested. The Ergosphere begins at the event horizon of a spinning black hole and extends outwards to a boundary known as the static limit. Inside this boundary, the dragging of spacetime is so intense, so overwhelmingly powerful, that it is literally impossible to stand still. Even to hover in one place relative to the distant stars would require you to travel faster than the speed of light, a clear violation of the laws of physics. You have no choice. The moment you cross into the Ergosphere, you're caught in its current. You're swept along with the black hole's rotation, a helpless vessel in a gravitational hurricane. But here is the crucial mind-bending difference. Unlike the event horizon, the Ergosphere is not a one-way trip. It is a treacherous domain, a cosmic rapids of the highest order, but it is a place from which escape is in principle possible. You can enter its swirling currents, ride the terrifying wave of warped space-time, and if you have enough energy and the right trajectory, you can fight your way back out into the calmer waters of normal space. The Ergosphere is a place where you are forced to dance to the black hole's tune, but the dance does not have to be fatal. It is a cosmic no-fly zone where the rules of navigation are rewritten. Your ship's engine may be firing in one direction, desperately trying to pull you away, but the current of spacetime itself could be carrying you sideways in a grand circle around the black hole. You're not just moving through space anymore. Space itself is moving you, carrying you on its inexorable tide. This bizarre reality, this zone of inescapable motion that is nevertheless escapable, is what transforms the black hole from a mere sink of energy into a potential source. It was a riddle that tantalized one of the greatest minds of the 20th century. In 1969, the mathematical physicist Roger Penrose, a thinker renowned for his deep and intuitive grasp of the geometry of spacetime, contemplated the strange properties of the Ergosphere. He saw not just a curiosity of general relativity, but an opportunity, a loophole in the universe's energy budget. He imagined a civilization advanced beyond our wildest dreams standing at the edge of this cosmic whirlpool. They would not see a monster. They would see a battery, a colossal spinning flywheel containing more energy than all the stars in their galaxy combined, stored in the pure rotational momentum of the black hole. And Penrose devised a theoretical mechanism, an audacious cosmic heist, for how they might tap into it. He wondered, could you throw something into the Ergosphere and have it come out with more energy than it had when it went in? Could you in effect steal a fraction of the black hole's spin, converting its rotational energy into usable power? The scheme he envisioned, now known as the Penrose Process, is both elegant and daring. It involves sending a vessel or a projectile into the Ergosphere on a carefully calculated trajectory. Once inside this swirling region of space-time, the vessel would split into two pieces. One piece would be sacrificed, aimed directly into the event horizon, a carefully chosen tribute to the beast. By falling into the black hole on a specific negative energy trajectory, this piece effectively subtracts mass and momentum from the singularity. The other piece, meanwhile, would be kicked away by the recoil from this separation. It would be violently flung back out of the Ergosphere, riding the wave of frame dragging like a cosmic surfer. When it merged back into normal space, if the maneuver was performed correctly, it would be moving faster, carrying significantly more kinetic energy than the original vessel had when it first entered. The energy would not have been created from nothing. It would have been stolen directly from the black hole itself. Each successful execution of this process would slow the black hole's rotation by an infinitesimal amount, tapping its vast reservoir of power. The black hole would act as a cosmic flywheel, and we would have found a way to harness its spin. This idea, born from the abstract world of mathematics, opens a breathtaking panorama of possibilities. We are forced to reconsider everything we thought we knew about these celestial objects. Are they truly the universe's graveyards, or could they be its powerhouses? Could an advanced civilization build a megastructure around a spinning supermassive black hole, creating a gargantuan power station to fuel an entire galactic empire for billions, even trillions of years? Could they toss their waste into the Ergosphere and in return receive a blast of pure, clean energy? This is no longer just physics. It is the stuff of cosmic engineering of science fiction, made manifest through the strange and beautiful laws of our universe. The implications are staggering. Perhaps some of the most violent and energetic phenomena we observe in the cosmos, like the colossal jets of plasma fired from the hearts of distant quasars, are not just the death cries of consumed matter. Perhaps they are natural large-scale examples of the Penrose process at work, the universe itself, tapping the rotational energy of its own black holes to create the brightest beacons in the night sky. The black hole, the object we once defined by its ability to take everything and give nothing back, might hold the secret to immense, almost infinite power. It presents us with the ultimate paradox, a machine of perfect efficiency, hidden inside a monster of perfect destruction. It is a cosmic engine fueled by the death of a star, a spinning dynamo of pure space-time waiting for someone or something to discover its secret and unlock its potential. The question then is no longer simply what a black hole is, but what it can become. How would one navigate the treacherous currents of the Ergosphere? What kind of materials, what kind of technology could possibly withstand such an extreme environment? And what would it truly mean for us, a fledgling species on a small blue planet, to one day have the capacity to harness the might of a spinning singularity? We stand on the shore of an ocean of possibility, looking out at a horizon that is both terrifying and utterly captivating. The beast may be a monster, but it may also be our salvation. The quest to understand if we can truly steal its fire to tame gravity's spinning heart has begun. Imagine a fire that burns forever, but consumes no fuel, an engine that generates colossal power, not from what it takes in, but from the very structure of reality itself. Our deepest understanding of the universe tells us such a machine is impossible, a brazen violation of the most sacred laws of energy conservation. And yet, we believe we have found one. Not in a laboratory, not in the realm of science fiction, but churning in the darkest, most violent corners of the cosmos. To find it, we must journey to the edge of imagination, to a place where space and time dissolve into a raging gravitational sea. We must journey to a black hole. For most of scientific history, our portrait of these cosmic monsters was one of brutal simplicity, a picture painted in the starkest monochrome of absolute gravity. This was the black hole conceived by Karl Schwarzschild, a German physicist wrestling with Einstein's brand new equations of general relativity, not in the quiet of a university study, but in the mud and chaos of the World War I trenches. He envisioned a star so massive, so crushingly dense, that its own gravity would cause it to collapse catastrophically in on itself, punching a hole through the very fabric of existence. The result was a gravitational singularity, an object of zero volume and infinite density, a mathematical nightmare given physical form. This Schwarzschild black hole was a model of terrifying perfection. It was perfectly spherical, utterly featureless, and completely unnervingly still. It did not spin, it did not move, it simply was. A silent passive drain at the bottom of the universe. Its sole defining characteristic was its boundary, a line of no return we call the event horizon. Picture this horizon not as a physical surface you could touch, but as a fatal threshold, a one-way door in space-time. It is the precise distance from the central singularity, where the gravitational pull becomes so overwhelming that the escape velocity equals the speed of light. Step 1 millimeter closer, cross that invisible demarcation, and you have committed yourself to the abyss. No engine, no force, no power in the known universe could save you. Even light, the fastest thing that exists, is captured and extinguished. For a Schwarzschild black hole, the story was this simple, this final. It was a cosmic prison from which nothing, not even information, could ever escape. It was an endpoint, a place where the universe's most complex phenomena were ground down into a simple, inescapable point. It consumed matter and energy, growing ever more massive, but it offered absolutely nothing in return. It was a glutton, a taker, the ultimate symbol of cosmic entropy and decay. For 50 years, this was our definitive, unchallenged image of a black hole, a static, dead object, a ghost of a star haunting the cosmic graveyard. It was a profoundly disturbing and deeply elegant idea, and it was almost completely wrong. The universe, as we have come to understand it, is never truly still. Galaxies pirouette in a dance that lasts for billions of years. Stars are born from swirling nebulae, their spin, a birthright inherited from their parent cloud of gas and dust. Planets orbit and rotate, their days and years a testament to this primordial momentum. Everything from the largest superclusters to the smallest subatomic particles possesses spin. It is one of the most fundamental properties of matter, so why would a black hole, the collapsed remnant of a giant spinning star, be any different? It seemed a glaring contradiction, a flaw in our perfect static model. If the star that birthed the black hole was spinning, where did all that tremendous rotational energy go? The laws of physics demand that angular momentum must be conserved. It cannot simply vanish. It must be accounted for. The problem was that Einstein's equations were so fiendishly complex that finding a solution for a spinning gravitational object seemed impossible. For decades, the world's greatest minds struggled with the puzzle and failed. Then, in 1963, a brilliant but unassuming New Zealand mathematician named Roy Kerr did the impossible. He found the solution. He solved the equations that had stumped even Einstein, and in doing so, he shattered our simple picture of the black hole forever. He gave us the Kerr black hole. This was not the silent, motionless ghost of Schwarzschild's equations. This was a dynamic, terrifying, and unbelievably powerful cosmic engine. The Kerr black hole spins, and in some cases it spins at almost incomprehensible speeds, whirling at a significant fraction of the speed of light. This rotation changes everything. It doesn't just add a new variable, it introduces a completely new dimension of physics, a phenomenon so bizarre it sounds like a fever dream. It gives rise to something called frame dragging. To understand what this means, you must first discard your everyday intuition about space. We tend to think of space-time as a passive backdrop, a static stage upon which the cosmic drama unfolds. General relativity teaches us this is wrong. Space-time is not a stage, it is an active participant. It is a dynamic, malleable fabric that can be warped, bent, and stretched by the presence of mass and energy. A planet like our Earth creates a gentle depression in this fabric, like a bowling ball resting on a rubber sheet. This curvature is what we feel as gravity. Now imagine that bowling ball is not just sitting there but is spinning rapidly. It won't just create a static dimple in the sheet. Its rotation will begin to grip the fabric around it, twisting it, dragging it along for the ride. The rubber sheet itself will start to swirl, creating a gentle vortex around the spinning ball. This is frame dragging, or the lens-thirring effect in its most basic form. The rotation of a massive object literally twists the fabric of space-time itself. On Earth, this effect is almost imperceptibly small, so minuscule that it took an incredibly sophisticated NASA experiment, Gravity Probe B launching 4 of the most perfectly spherical gyroscopes ever created to measure the infinitesimal twist of our planet's rotation on the local space-time grid. The result, after decades of work, confirmed Einstein's prediction. The Earth drags space-time with it by the barest, most delicate fraction. But around a Kerr black hole, this is no delicate infinitesimal effect. It is the single most dominant force in its environment. Here, a mass billions of times greater than our Sun is spinning at nearly the speed of light. It does not just gently twist space-time, it seizes it, churns it, and whips it into a furious, inescapable vortex. The very geometry of reality is caught in its grip. This is not like being caught in the wind or a current in the ocean, which are movements of matter through space. This is the movement of space itself. The stage is no longer stationary. It has become a violent spinning carousel. This violent twisting of space-time creates a new, utterly bizarre region around the black hole, a region that does not exist for its non-spinning Schwarzschild cousins. It's a place called the Ergosphere. The word comes from the Greek ergon, meaning work, and it is here in this sliver of violently contorted reality that the laws of physics seem to bend and the impossible becomes real. The Ergosphere lies outside the event horizon. This is a critical distinction. You can in principle enter the Ergosphere and then leave again. You are not yet doomed, but you're no longer free. The outer boundary of this region is called the static limit. It is the point where the rotational drag of the black hole on space-time becomes so powerful that it is moving at the speed of light. Inside this boundary, inside the Ergosphere, space-time is being pulled along faster than light. Think about what this means. To stand still in the universe, to have zero velocity relative to the distant stars, you would need to travel faster than light in the opposite direction of the spin. This is of course impossible. Nothing can travel faster than light through space. Therefore, within the Ergosphere, standing still is forbidden by the laws of the universe. You have no choice. You're swept along by the current of space-time itself. You could have the most powerful rocket engines imaginable pointed directly away from the black hole, burning with all their might, just to hold your position, and you would still be dragged inexorably around the black hole along with its spin. You're a swimmer trying to fight your way upstream against a torrent that is moving faster than you could ever hope to swim. Your struggle is futile. The river of space-time carries you onward. It is a place where space has a velocity, where location itself has momentum. The Kerr black hole is a cosmic dynamo, a gravitational gyroscope of unimaginable power, and the Ergosphere is its field of influence, a bubble of reality, where the normal rules of motion are utterly suspended. The spinning mass of the black hole has imbued the space around it with a colossal amount of rotational energy. The Ergosphere is in effect a giant reservoir of kinetic energy, stored not in any physical matter but in the pure geometry of twisted space-time. This region is a maelstrom. Inside the two horizons of the Kerr black hole, an outer and an inner event horizon hide a ring-shaped singularity, a stark contrast to Schwarzschild's simple point. The physics here is a chaotic tempest of tidal forces and distorted light where time and space are warped to their breaking points. It is a place of profound violence, and yet it holds a tantalizing promise. A paradox that has captivated physicists for half a century. The event horizon we know is the ultimate one-way street. Anything that crosses it adds its mass and energy to the black hole lost to our universe forever. But the Ergosphere is different. You can enter it, and you can escape. Which leads us to the most profound and consequential question of all. If you enter this spinning vortex of pure energy, this region, where space-time itself is your propellant, and then you manage to escape, what happens? Can you emerge from this gravitational storm with more energy than you had when you went in? Could you in essence steal energy, not from the black hole's mass, but from its spin, tapping into the most powerful rotational engine in the cosmos? Could you against all logic get something for nothing by playing a game of cosmic chicken with the edge of eternity? The answer astonishingly seems to be yes. But the method for achieving this cosmic heist requires a maneuver so clever, so audacious, it sounds like it was pulled from the pages of a madman's diary. And so this swirling vortex of captive space-time, this Ergosphere, was not initially seen as a place of opportunity. For most physicists in the mid-20th century, it was simply a mathematical curiosity, another terrifying feature of the universe's most extreme object. The black hole was the ultimate endpoint, a singularity of utter finality from which nothing, not even a whisper of information, could return. The popular imagination, and indeed much of the scientific consensus, had painted these gravitational titans as cosmic predators, hungry ghosts that consumed matter and energy with an insatiable appetite, giving nothing back. They were sink drains at the bottom of the universe where the laws of physics went to die. But within the quiet, methodical world of theoretical physics, one mind was looking at the same equations and seeing not an ending but a source. He saw not a tomb but an engine of unimaginable power. That mind belonged to a brilliant English mathematician, a geometer of space-time named Roger Penrose. In the late 1960s, a golden age for relativity when the cosmos was being rapidly reimagined through the lens of Einstein's equations, Penrose possessed a unique gift. He could visualize the esoteric four-dimensional landscapes of general relativity with an artist's intuition. Where others saw impenetrable arrays of symbols, he saw flowing surfaces, twisting geometries, and causal structures of breathtaking elegance. He wasn't just solving equations, he was exploring a hidden architecture of reality. And in 1969, he turned his formidable intellect toward the spinning heart of a Kerr black hole, asking a question so audacious, so contrary to all accepted wisdom, that it bordered on scientific heresy. What if you could take something from a black hole? What if instead of being a cosmic vacuum cleaner, a rotating black hole was actually a celestial battery, a stupendous reservoir of energy waiting to be tapped? His proposal, published in a paper that would ripple through the world of astrophysics, was not born of fantasy, but of the rigorous logic of physics itself. It became known as the Penrose Process, a thought experiment of such profound elegance that it felt less like an invention and more like a discovery of a deep cosmic secret. Penrose imagined a civilization advanced enough not just to travel to the doorstep of a black hole, but to engineer a mission into the very heart of its rotational fury. He asked us to picture a vehicle, a probe, a simple particle, let's call it our traveller, as it approaches this gravitational behemoth. Its mission is not to study, but to steal. Its target is the Ergosphere, that chaotic region we've just explored, where space-time itself is dragged along at nearly the speed of a light. Let's follow our traveller. We arm it with a carefully calculated trajectory, aiming not for the black hole itself, but for this swirling region just outside the point of no return. As it crosses the stationary limit, the outer boundary of the Ergosphere, the experience is instantaneous and absolute. Our traveller is immediately caught in a gravitational whirlpool of incomprehensible force. It can no longer remain still relative to the distant stars. To do so would require moving faster than light against the current of space-time and impossibility. It is now a boat caught in the universe's most powerful rapids, forced to orbit in the same direction as the black hole's spin. The entire fabric of reality here is a flowing, unstoppable medium, and our traveller is now part of that flow. The energy of this region is immense, a maelstrom of kinetic and potential energy, bound up in the black hole's colossal angular momentum. But this energy is chaotic, untamed. The challenge is not in finding it, but in capturing it. This is where Penrose's genius reveals itself. He realized you couldn't just dip a bucket into this river of space-time and pull out energy. You had to perform a maneuver of exquisite precision and timing. Deep within the Ergosphere, perilously close to the event horizon, our traveller must perform a single critical action. It must split in two. Imagine it as a spacecraft jettisoning a payload or a capsule firing a retro rocket. It separates into two distinct fragments, which we will call the offering and the escapee. This separation is not a random explosion. It is a meticulously planned event designed to exploit the bizarre physics of this unique location. The offering by design is propelled directly backward against the violent current of space-time. It is a sacrificial piece, a payment to the cosmic abyss. Its trajectory is carefully angled so that it crosses the one boundary from which there is no escape. It falls through the event horizon. For an observer watching from a safe distance, something truly strange has just happened. Because the offering was fired backward within a region of space-time already moving forward at incredible speed, its trajectory can be arranged in such a way that its total energy as measured by us is negative. This is one of the most counterintuitive ideas in all of physics, yet it is a direct consequence of Einstein's equations. Think of it like this. Imagine you're on a train moving at 100 km per hour and you throw a ball backward at 110 km per hour. To someone standing on the ground, the ball is actually moving backward at 10 km per hour. You on the train have given it energy, but from an external perspective it has a negative velocity relative to your own initial motion. The Ergosphere is a far more extreme version of this. By being thrown backward inside this forward-dragging space-time, the offering can be manipulated to carry a negative energy value into the black hole. It is a debt and energy loan that the black hole is forced to accept. The moment the offering vanishes beyond the event horizon, its fate is sealed. It will be crushed into the singularity its matter added to the black hole's mass. But its negative energy has a profound consequence. According to the unbreakable laws of thermodynamics and conservation of energy, if you add negative energy to a system, the total energy of that system must decrease. The black hole has been forced to pay the offering's debt. But where does it get the energy to pay? It comes from the only available source, its own rotation. The offering acts like a cosmic brake, a tiny anchor dropped into a spinning flywheel the size of a solar system. It drags against the black hole's spin, robbing it of an infinitesimal amount of its angular momentum. The black hole, in exchange for swallowing this sacrificial fragment, is forced to spin down just a tiny bit. Its rotational energy has been diminished. Now consider the fate of the second fragment, the escapee. By the law of conservation, if one piece flew off with negative energy, the other piece must fly off with a corresponding surplus of energy to keep the total balanced. This isn't just a small boost. The escapee is violently ejected from the ergosphere, flung away from the black hole with ferocious speed. When we, observing from our safe distance, finally measure its energy, we find something miraculous. The escapee now possesses more energy than our entire original traveller had when it first began its journey. It has not created energy from nothing which would violate the laws of physics. No, it has performed an act of cosmic larceny. It has successfully siphoned off a fraction of the black hole's rotational energy and converted it into its own kinetic energy. The energy lost by the black hole's spin has been transferred directly to our escaping fragment. We sent in a particle with a certain amount of energy, sacrificed a piece of it, and received a different piece back with a net profit. We have stolen energy from a black hole. This revelation was transformative. Penrose's elegant thought experiment single-handedly shattered the paradigm of the black hole as a purely destructive entity. It was no longer just a gravitational monster, a one-way ticket to oblivion. It was now, at least in theory, a dynamic engine. The ergosphere was its exhaust port, a place where its colossal rotational power could be accessed. The process revealed that a black hole's energy is stored in two forms: its irreducible mass, which can never decrease, and its rotational energy, which can. Penrose had discovered the theoretical key to unlocking that rotational vault. A spinning black hole, he showed, could be a source of power, dwarfing the output of 1 billion suns. A single supermassive black hole at the centre of a galaxy contains more rotational energy than the entire galactic stellar population will radiate over millions of years. It is perhaps the single greatest concentration of usable energy in the entire universe. The implications were staggering, sounding more like science fiction than theoretical physics. One could imagine an advanced civilization building a vast industrial complex around a spinning black hole. They could continuously send in pellets or probes, splitting them in the ergosphere, sacrificing one half to the event horizon while collecting the energized half. The black hole would become their power plant, a gravitational gyroscope of unimaginable scale. They could use this process to power their entire civilization for eons, all while methodically slowing the black hole's spin. Eventually, after countless repetitions, they could slow it all the way down, until it stopped spinning entirely, becoming a static, non-rotating Schwarzschild black hole. At that point, the ergosphere would vanish, the cosmic battery would be depleted, and the process would no longer work. They would have mined the black hole for all its available rotational power. Suddenly, the universe felt different. The most terrifying objects it contained now held a glimmer of promise. Penrose hadn't just solved a set of equations, he had given us a new way to see. He had recast the villain of the cosmic story as a potential benefactor, a dark, sleeping giant whose power was not just for destruction, but could in principle be harnessed for creation. He replaced the image of the cosmic vacuum cleaner with the image of a cosmic flywheel, a repository of primordial energy from the formation of the galaxy itself. The process was a stunning proof of concept, a testament to the power of human intellect to grapple with the universe's most profound mysteries and find unexpected hope in its darkest corners. The physics was sound, the mathematics impeccable. The theory stood as a monumental achievement in our understanding of gravity. But as the initial shock and awe settled, a new, more pragmatic set of questions began to emerge. A theory on paper is one thing. The monumental, terrifying reality of engineering such a feat is quite another. Could anyone or anything ever truly build the machinery to tame such a beast? And so the Penrose Process stands before us, a breathtakingly clever piece of cosmic theft. A single, well-aimed particle shattered in just the right way within the ergosphere can escape with more energy than it had when it entered. The price for this impossible gain is paid by the black hole itself, a tiny, infinitesimal fraction of its rotational momentum lost forever to the void. It's an elegant, almost mischievous solution to an abstract puzzle. But as you stand here contemplating this single transaction, this one grain of sand exchanged on a cosmic shore, you must be asking the same question that haunted physicists. Is this it? Is this grand cosmic loophole, this secret door in the laws of physics, merely a curiosity for a hypothetical hyper-advanced civilization to exploit? Or is nature, in its infinite and often violent imagination, already putting this principle to work on a scale so vast it defies comprehension? To find the answer, we must pull our gaze away from the solitary particle and look out towards the deepest, most ancient corners of the universe. We look towards beacons of impossible light shining from the dawn of time. They are called active galactic nuclei, or AGNs, and their most extreme brethren, the quasars. These are not stars, nor are they galaxies in the familiar serene sense. They are galactic cores gone wild, powered by supermassive black holes billions of times the mass of our Sun, furiously consuming entire star systems. Yet from the very heart of this ultimate darkness, this gravitational abyss, something extraordinary emerges. From the poles of these spinning gravitational monsters, two colossal pillars of light erupt. They are not light in the conventional sense, but focused coherent jets of plasma, streams of matter heated to millions of degrees and accelerated to over 99% the speed of light. These are celestial blowtorches of unimaginable ferocity. They are so enormous that they often dwarf the very galaxies that host them, stretching for hundreds of thousands, sometimes millions of light years into intergalactic space. Imagine a beam of energy fired from the center of our Milky Way that extends 5, 10, even 20 times the entire diameter of our galaxy. They are perfectly straight, held in place by some unseen force like luminous lances hurled by a god spearing through the cosmic darkness. And for millions of years they blaze with the energy of 1 trillion suns. Here lies a paradox so profound it should stop you in your tracks. We have just spent our time together understanding the black hole as the universe's ultimate endpoint, a one-way membrane from which nothing, not even light, can return. It is the great taker, the final destination. How then can this region of space, defined by its inescapable gravity, also be the launch pad for the most powerful, most energetic and most sustained explosions the universe has ever known? How can the universe's greatest sink also be its most prodigious fountain? The simple, particle splitting of the Penrose Process, as elegant as it is, cannot be the answer. The efficiency is far too low. Throwing individual rocks into the ergosphere would be like trying to empty an ocean with a thimble. The energy unleashed in these quasar jets is titanic monumental. It requires a mechanism of almost perfect power conversion, a way to tap the black hole's rotational energy far more effectively. Nature needed a better tool. And it found one in the most fundamental force of the cosmos after gravity itself, electromagnetism. The secret lies not just within the ergosphere, but in the chaos that surrounds it. A supermassive black hole is never alone. It is encircled by a swirling, flattened vortex of doomed matter known as an accretion disk. This is a city of stars, gas and dust, all caught in a final frantic gravitational dance before plunging past the event horizon. As this material spirals inward, friction and tidal forces heat it to incandescent temperatures hotter than the core of any star. It doesn't just glow, it blazes with high-energy radiation, becoming the luminous matter that makes quasars visible across billions of light years. But this inferno of superheated gas is not just gas. It is a plasma, a turbulent sea of charged particles, protons and electrons stripped from their atoms and moving at tremendous speeds. And wherever you have moving electric charges, you inevitably get magnetic fields. The accretion disk then is not merely a cosmic drain. It is a dynamo of unimaginable power. It spins and churns, generating magnetic fields so intensely strong they would beggar all description, 1 trillion times more powerful than the field of our own Earth. These magnetic field lines born in the disk don't just stay there. They rise up from it, looping through space like immense invisible arches, some of which thread directly through the ergosphere and even across the event horizon itself. And this right here is the crucial connection. This is where Roger Penrose's theoretical insight meets the violent reality of the cosmos. In 1977, two brilliant astrophysicists, Roger Blandford and Roman Znayak, realized that these magnetic fields were the missing piece of the puzzle. They were the gear, the transmission that could connect the raw rotational power of the black hole to the universe outside. What they proposed was a mechanism of sublime power, an extension of Penrose's idea from a single particle to the very fabric of space-time and magnetism. It begins with the frame dragging we witnessed earlier, that relentless twisting of space caused by the black hole's rotation. This is the engine's flywheel. Now picture those immensely powerful magnetic field lines rising from the inner edge of the accretion disk and piercing the ergosphere. In our normal everyday experience, magnetic fields are intangible. They pass through things. But in the realm of general relativity near a spinning black hole, the rules change. The space-time within the ergosphere is being dragged around so violently that it behaves like a physical rotating conductor. It grabs onto the magnetic field lines, it seizes them. The field lines become in a sense frozen into the swirling vortex of space-time itself. As the black hole spins, its ergosphere relentlessly twists these magnetic lines of force. Imagine holding a set of elastic bands with one end anchored in the distant stable accretion disk and the other end being furiously wound up by a spinning top. The bands coil tighter and tighter, stretching and storing immense amounts of tension of potential energy. This is what the Blandford-Znayak process describes. The black hole's rotational energy, the very energy Penrose sought to steal, is being converted. It is being systematically drained from the black hole and stored in the tension and twisting of the surrounding magnetic field. The ergosphere acts as a colossal cosmic circuit, a power converter of perfect efficiency, transforming gravitational energy into electromagnetic energy. This magnetic field, now coiled into a stupendous spring of power, is wound tightest along the path of least resistance, the black hole's axis of rotation. Here above the north and south poles, the magnetic field lines are funneled into a tightly wound spinning tower of pure electromagnetic potential. This tower does not remain passive. The energy cannot build forever. It becomes a cosmic particle accelerator, a magnetic nozzle of galactic proportions. It latches onto the charged particles, the electrons and positrons boiling off the turbulent inner edge of the accretion disk. And then, with all the force of a spinning singularity behind it, it flings them outward. The tightly coiled magnetic field acts like a guide wire, a barrel of a cosmic gun, focusing this escaping matter into two perfect narrow beams. These are the jets we see. They are not an explosion in the traditional sense. There is no single bang. They are a continuous, focused, sustained channeling of power, a direct feed from the spin of the black hole itself. The material in the jet did not come from inside the black hole. It never crossed the event horizon. It is material from the accretion disk that was destined for oblivion, but was rescued at the last possible moment and empowered by the black hole's own dying spin. Every particle accelerated, every joule of energy that blazes across 1,000,000 light-years is paid for by the black hole's rotation. The jets are actively slowing the black hole down. Over millions of years, this process acts as a brake, gradually transforming a rapidly spinning Kerr black hole into a slower, less energetic one. We are witnessing, written in letters of fire across the cosmos, the Penrose process executed by nature itself. The ergosphere is not just a theoretical playground, it is the active powerhouse for the most luminous objects in creation. Let the scale of this sink in for a moment. The energy output from a single quasar jet can outshine all 100 billion stars of its host galaxy combined. Not for a second, not for a year, but continuously for millions of years. It is a torrent of power so vast that if you could capture the energy released by one of these jets for a single second, it would be enough to power all of human civilization at its current rate of consumption for a period longer than the Earth has existed. And all of this power originates from that strange whirling region of space-time, that gravitational vortex just outside the point of no return. The theory is no longer just lines in an equation. We see its consequences. We have photographed its handiwork. The Hubble Space Telescope, the Chandra X-ray Observatory, the new James Webb Space Telescope, they all return the same incredible images. Galaxies adrift in the darkness with brilliant lances of pure energy erupting from their cores, a testament to the engine whirring away in the unseen centre. We can even see the damage these jets inflict upon the universe around them. As they plough through intergalactic space, they heat up and ionize vast clouds of gas, carving out enormous cosmic bubbles and potentially disrupting the formation of new stars hundreds of thousands of light years away from their source. They are galactic weather systems shaping the very evolution of the galaxies they inhabit. This is the pivotal moment in our understanding. This is where the black hole ceases to be a mere gravitational sinkhole, a passive dead object defined only by what it consumes. The discovery of the Ergosphere's role as an engine forces us to see the black hole for what it truly is, one of the most dynamic, active and influential objects in the cosmos. It is a cosmic flywheel storing the angular momentum from every star and gas cloud it has ever swallowed. And through the sublime physics of its ergosphere, it can release that stored energy in a controlled, focused and devastatingly powerful way. It is the heart of the galaxy, not just gravitationally but energetically. It takes in the old and the dead, the spent stars and the stray gas, and in return it breathes fire back out into the cosmos, a form of cosmic recycling on the grandest imaginable scale. The abstract notion of stealing energy from a black hole is no longer science fiction. The universe has been doing it for 13 billion years. The ergosphere, that once baffling prediction of a purely mathematical theory, has been revealed as a tangible place. A place where space-time itself is the machinery. A place where gravity is converted into light. A place where the end of everything becomes the beginning of the most violent spectacles the universe can muster. So we have found nature's own method for tapping this incredible power source, a messy, violent and beautiful process involving magnetic fields on a galactic scale. The evidence is undeniable, written in the light of distant quasars. But it leaves us with an even more tantalizing thought. If nature can devise such a mechanism born from the chaos of a feeding black hole, what could intelligence do? What would happen if a civilization far beyond our own decided to move beyond nature's brute force approach and engineer this process directly? Could we build a structure, a machine around the ergosphere designed to harness this rotational energy with perfect quiet efficiency? And what would a society powered by a black hole even look like? The question is no longer if. We can steal energy from a black hole, but how we might one day build the bucket to carry it home. We have seen the universe itself perform the miracle. We've witnessed the jets of quasars, those incandescent lances hurled across intergalactic space powered by this very engine. Nature on its grandest and most violent stage has shown us the principle, a blueprint written in the language of plasma and gravitation. The potential hums in the fabric of space-time, a promise of energy so vast it could cradle 1,000 civilizations. But to witness a star-swallowing monster perform a trick is one thing. To step into the cage and tame it is another entirely. The chasm between cosmic demonstration and human application is wider and deeper than any abyss we have ever dared to contemplate. Here in the shadow of the event horizon, our ambition collides with the most brutal and unforgiving laws of reality. The question shifts from what is possible to a far more humbling, far more terrifying inquiry: what is survivable? Imagine our vessel a triumph of future engineering making its final approach. Long before we even glimpse the ergosphere, the universe begins to protest our intrusion. The first sentinel of the black hole's dominion is not a wall of fire, but a silent, invisible assassin, the tide of gravity. On Earth, the moon's gentle pull creates our ocean tides a difference in force across our planet of mere inches. But here, approaching a spinning, supermassive singularity, that gentle caress becomes a rack, a cosmic instrument of torture. The gravitational force on the nose of your ship would be exponentially stronger than the force on its tail. This differential is not a strain, it is an execution. Any object with physical dimension is seized, stretched, and relentlessly pulled apart. A steel girder would be drawn out like warm taffy. The crystalline structure of the most resilient alloy would shatter its atomic bonds, screaming and then snapping under the impossible tension. Your own body would be elongated into a stream of atoms, a process scientists so clinically, so chillingly call spaghettification. Our vessel cannot simply be strong. It must somehow negate physics itself. It must possess an active structural integrity field, a theoretical concept that pushes and pulls on its own hull with perfectly calibrated force, counteracting the black hole's grip at every single point from the outer skin to the innermost wiring. A gravitational gyroscope constantly adjusting, fighting a war of attrition against a force that does not tire. And even if we could survive being torn asunder, we must navigate a labyrinth where the map is constantly rewriting itself. We think of an orbit as a clean, predictable ellipse, a cosmic dance choreographed by Newton and refined by Einstein. But near a spinning black hole, this dance becomes a chaotic frenzy. Space-time itself is not static. It is a swirling vortex, a whirlpool being dragged along by the black hole's immense rotation. There are no stable orbits in the conventional sense. Every trajectory is a decaying spiral, a one-way trip towards the horizon. To simply stay in place to hover would require an engine output equivalent to the continuous detonation of a star. Our navigation cannot be reactive, it must be predictive on a quantum level. A superluminal computer core running trillions of simulations per second would be needed to chart a course through these gravitational rapids. It would need to calculate our path not through 3 dimensions of space, but through 4 dimensions of a violently contorted space-time, where time flows at a different rate for every part of our ship. A single miscalculation, a rounding error in the 15th decimal place, and our carefully planned trajectory becomes a terminal plunge. We would simply be erased from the universe, our final moments stretched into an eternity for a distant observer who sees us frozen in time, painted against the blackness of the abyss. Let us assume we solve these problems. We build the indestructible ship. We invent the prescient navigator. We survive the tides and the temporal distortions. Now we face the dragon's fiery breath. For many of the most powerful, rapidly spinning black holes are not isolated in the sterile vacuum of space. They are feeding. They are surrounded by a chaotic incandescent halo of captured material, the accretion disk. This is not the gentle glowing ring of Saturn. This is a celestial maelstrom of gas dust and shattered stars, all accelerated to nearly the speed of light as they spiral towards their doom. Friction and magnetic turbulence within this disk heat the material to temperatures of millions, even billions of degrees. It becomes a colossal burning platter of plasma, outshining the combined light of every star in its host galaxy. To approach the Ergosphere, we must fly through this furnace. The radiation bath is so intense it defies all terrestrial comparison. It is a continuous omnidirectional blast of X-rays and gamma rays, a storm of high-energy photons that would sterilize planets and scour life from entire solar systems. Any conventional shielding, even meters of solid lead, would be vaporized in an instant, not by heat, but by the sheer energy of the bombardment. The radiation pressure itself, the physical push of the light, would act like a solid wall, requiring immense thrust just to push through it. Our crew would be cooked alive, their DNA shredded in microseconds. Our ship's electronics would be fried, its computer systems reduced to fused slag. How do we shield against the wrath of a captured galaxy? The answer cannot be found in matter alone. We cannot build a wall thick enough. We must build a shield of pure force. Perhaps a magnetic bubble, a magnetosphere, thousands of times more powerful than Earth's, could deflect the charged particles of the plasma. But it would do nothing against the onslaught of neutral photons, the X-rays and gamma rays that carry no charge. For that we need something even more exotic. A theoretical plasma window. A contained layer of ultra-dense gas held in place by magnetic fields could potentially absorb the incoming energy, glowing white-hot, but protecting the vessel within. Or we might turn to the very physics we are fighting. Could we generate a localized distortion in space-time just ahead of our ship, a gravitational bow shock that bends the path of the deadly radiation around us? We would be surfing on a self-generated wave of warped reality, cocooned in a bubble of safety we ourselves have forged. The engineering is no longer about nuts and bolts. It is about the mastery of the fundamental forces, about building with gravity, energy, and space-time itself. Let us say we succeed. We have navigated the tides, surfed the vortex, and pierced the wall of fire. We have now arrived. We cross the stationary limit and enter the Ergosphere. Here the true strangeness begins. Inside this region, space-time is dragged forward faster than the speed of light. This does not mean we are breaking Einstein's laws. Rather, it means that space itself is moving and we are carried with it. To stand still relative to the outside universe is physically impossible. No amount of engine power could hold you in place. You're on a cosmic treadmill that cannot be turned off. You must move in the direction of the black hole's spin. It is from this forced inexorable motion that we can steal our power. Now the heist, the delicate and blisteringly fast maneuver at the heart of our mission, must be executed with impossible precision. Our ship opens its payload bay. It ejects a carefully chosen mass, our sacrificial package. This could be anything: a dense block of refined metal, an automated drone, or perhaps in an act of cosmic poetry, the accumulated nuclear waste of our civilization. We are not just generating power, we are cleaning our celestial backyard. The trajectory of this package is critical. It must be launched against the direction of the black hole's spin. This is the key. By doing so, it enters a negative energy orbit as defined by the bizarre physics of the Ergosphere. For an outside observer, this is a mathematical abstraction. For the package itself, it is a death sentence. It is immediately captured by the black hole, its path curving irrevocably downwards, past the point of no return. It crosses the event horizon. Its mass and its negative orbital energy are added to the black hole. But Newton's third law, for every action there is an equal and opposite reaction, still holds true even in this mangled version of reality. As the package with negative energy falls in, an equal amount of positive energy is imparted to our ship in the form of a colossal kick of momentum. We are flung outwards, catapulted away from the abyss. We emerge from the Ergosphere moving significantly faster than when we entered. This increase in kinetic energy is not free. It is a direct payment drawn from the rotational bank account of the black hole itself. We have been paid to throw away our trash. But this transaction, this grand act of cosmic larceny, is not without consequence. There is no perpetual motion machine in the universe. Every watt of power we gain, every joule of energy we add to our civilization's grid, comes at a direct and measurable cost to the black hole. The energy we steal was stored as angular momentum. It was the spin. With each payload we sacrifice, with each successful extraction, the black hole slows down. Its rotation, once a furious blur, becomes infinitesimally more sedate. This is the cosmic tax on our power. We are draining the battery. The effect of a single mission would be negligible, like a single drop of water evaporating from an ocean. But a civilization running on this power for millennia, launching fleets of automated barges in a constant stream, would have a profound impact. As the black hole's spin decreases, the very source of our power begins to shrink. The Ergosphere is not a fixed entity. Its size is directly proportional to the black hole's rotational speed. A maximally spinning Kerr black hole has a large, generous Ergosphere, a vast reservoir of accessible energy. But as we bleed away its momentum, the boundary of the Ergosphere contracts. The stationary limit creeps closer and closer to the event horizon. The cosmic power plant, once sprawling and ripe for the taking, becomes smaller, more dangerous, and less efficient to tap. The game becomes harder. The margins for error shrink. The energy return on our investment diminishes with every passing century. Eventually, after an epoch of providing limitless energy, the process ends. Our civilization will have slowed the black hole to a complete stop. It will have transitioned from a dynamic spinning Kerr black hole to a static, non-rotating Schwarzschild black hole. And with that final imperceptible halt in its rotation, the Ergosphere vanishes. It ceases to exist. The cosmic engine shuts down. The free lunch is over. The space between the stationary limit and the event horizon is gone, swallowed by the horizon itself. There is no longer a region where we can play our clever games with negative energy. The power is cut off. The well is run dry. We are left with a quiet, placid monster, a simple point of infinite density, its wild, energetic youth stolen from it to power our cities and starships. This is the ultimate truth of the Penrose Process. It is not an infinite fountain. It is a finite inheritance, a cosmic trust fund bequeathed to us by the death of a massive star, and like any inheritance, once it is spent, it is gone forever. This realization forces upon us a question of profound importance, one that transcends engineering and enters the realm of philosophy. In our quest for energy, in our insatiable drive to expand and survive, are we prepared to become a species that consumes cosmic wonders? Are we willing to still the great gravitational gyroscopes of the galaxy to quench their fire and leave them dormant and diminished, all to keep our own lights burning for a few million more years? The power is there waiting in the darkness. But the price is not measured in resources or wealth, but in the very character of the universe we will leave for those who come after. The choice to harness this power is not just a technological challenge, it is a moral one written on the grandest possible scale. And so, we arrive at the precipice of our grand question, the very inquiry that has propelled us across light years of theory and into the deepest gravitational well in existence. Having charted the treacherous territory of the Ergosphere, having understood the audacious genius of the Penrose Process, we must finally ask it directly. Can we, a fleeting civilization of curious primates, truly reach into that spinning abyss and steal its fire? Can we harness the most powerful engine in the universe? The answer, delivered not with the sting of failure, but with the quiet wisdom of cosmic perspective, is a resounding and unequivocal "not yet." And perhaps not for a very, very long time. The engineering challenges we glimpsed are not mere hurdles. They are mountains whose peaks are lost in the clouds of a distant millennium. The materials required to build a structure that could survive the tidal stresses, the radiation, the sheer gravitational violence of a black hole's doorstep. These are materials that exist today only in the language of theoretical physics, forged from mathematics, not from matter. The precision needed to throw a payload into the Ergosphere, to have it split at the exact vector, at the perfect moment to then catch the escaping fragment. It's a feat of celestial archery, so demanding it makes landing a rover on Mars look like a child's game of catch. We are in this grand endeavour like ancient mariners staring at the moon, able to chart its phases and admire its light, but utterly lacking the vessel to cross the dark ocean that separates us. But to stop there would be to miss the entire point. It would be to mistake the destination for the journey. For the true value of this cosmic quest right now is not found in blueprints and alloys. It is found in the expansion of the human mind. The Ergosphere has ceased to be a mere abstraction, a curious footnote in Einstein's equations. It has become a crucible for our imagination, a place where the laws of physics invite us not to build, but to dream. And in those dreams, powered by the world's most advanced supercomputers, we are already sending our first probes into the storm. These are not probes of metal and wire, but of pure data. Digital ghosts flawlessly executing the Penrose process 1,000,000 times a second. Inside these virtual universes born from silicon and electricity, the cosmic drama begins. We can watch as a simulated particle, a single point of light, embarks on its fateful journey. We see it drawn in not by a simple pull, but by the irresistible vortex of frame dragging the space-time current itself. It is a dance, not a fall. The simulation allows us to color-code the energy potentials to see the Ergosphere not as a black void, but as a shimmering incandescent region of pure kinetic opportunity. Red for high energy, blue for low, our particle bathed in this crimson glow is filled to bursting with the rotational energy it has skimmed from the black hole itself. Then, at the precisely calculated moment, the schism. A package of waste, a carefully calibrated payload of negative energy is jettisoned. We watch its ghostly trajectory curve inward, crossing that fatal boundary of the event horizon forever lost to our universe. It is a sacrifice, a tribute paid to the gravitational titan, but in paying it, the conservation of energy demands a reward. The other half of our probe, the part we want, recoils with ferocious power. The simulation shows its colour shifting, flashing from red to a brilliant, impossible white. It has not just retained its own energy, it has absorbed the colossal momentum of the sacrificed piece, magnified by the black hole's spin. It is flung away from the abyss with more energy than it had when it began its journey. The theft is complete. The numbers on the screen don't lie. Energy has been extracted from the void. The machine works. Again and again, these simulations run each one a silent testament to the raw truth of the concept. Physicists can now model different black holes, small stellar mass spinners, and the supermassive titans at the heart of galaxies. They can adjust the angle of approach, the mass ratio of the split, the velocity of the initial particle. They are no longer just testing a theory, they are optimizing a process that we may not use for 10,000 years. They are writing the first chapter of an engineering manual for a future generation, a generation that may look back on us as we look back on those who first dared to dream of flight. These models reveal the staggering efficiencies possible. Under ideal conditions for a rapidly spinning Kerr black hole, the energy gain isn't just a few percent. It can be a monumental 100 and 200% or more an energy amplification that defies all of our terrestrial experiences. It's a confirmation written in the cool, clean language of code that the universe contains a free lunch of almost unimaginable proportions. This theoretical playground, however, has led physicists to contemplate scenarios far more dramatic than simply powering a futuristic city. It has led them to a concept so extreme, so violent, it sounds like it was ripped from the pages of science fiction. They call it the black hole bomb. Imagine for a moment you don't just want to send a single probe to steal a single packet of energy. Imagine you want to initiate a runaway chain reaction. The key theorists realized is a phenomenon called superradiance. It's the Penrose process, but for waves instead of particles. A light wave or a gravitational wave entering the ergosphere can also split. Part of the wave falls in with negative energy, and the rest is amplified, escaping with more energy than it started with. Now, what if you could trap that amplified wave? What if you could build a mirror around the black hole, a vast spherical, perfectly reflecting shell, encasing the entire spinning giant? When a stray light wave enters the ergosphere through a small opening, it gets amplified. It shoots back out, hits the mirror, and is reflected straight back into the ergosphere, where it is amplified again, and again, and again. Each round trip, its energy grows exponentially. It is a cosmic echo chamber, where the echo is always louder than the original shout. The energy inside the mirrored sphere would build at an astonishing, terrifying rate, feeding on the black hole's rotational fury, turning the space between the mirror and the event horizon into a celestial blast furnace of pure radiation. The pressure of this trapped, ever-amplifying light would become unimaginable until the entire structure either vaporizes or the architects of this bomb decide to open a window. The resulting beam of energy would be a celestial blowtorch of such intensity it could sterilize an entire solar system from light years away. This is not a power source. It is a thought experiment that reveals a profound and chilling truth. The ergosphere is not just a gentle reservoir of power, it is a coiled spring of cosmic proportions, and the mathematics of general relativity provides a trigger. We can find no flaw in the physics. A sufficiently advanced civilization, one that has mastered matter and energy, on a scale we can barely comprehend, could theoretically construct such a device. It serves as a stark reminder that the same cosmic principles that could one day power a utopian future could also be weaponized into the ultimate engine of destruction. The universe, it seems, is always neutral. It offers up its power, and it is the wisdom or folly of the user that determines its purpose. But let us turn away from such apocalyptic visions and dare to imagine a more hopeful, more magnificent future. Let us imagine a civilization not bent on destruction, but on creation and survival through eons. Such a civilization would eventually face an energy crisis that would make our own concerns over fossil fuels seem quaint. To power a truly interstellar society, to manipulate space-time, to compute on a galactic scale, you need a source of power that dwarfs the output of stars. You need a black hole. But how would you harness it in a controlled, sustainable way? The idea of a bomb is brutish and inefficient. The answer might be the ultimate expression of cosmic engineering, a structure that marries the concept of the Dyson sphere with the unique physics of a black hole. A traditional Dyson sphere envisioned to surround a star is a passive collector of light. A black hole Dyson sphere would be an entirely different beast. It would be an active participant in the energy extraction process. Picture a vast, intricate lattice of collectors' habitats and power stations, all orbiting within the gravitational domain of a supermassive black hole. This would not be a solid shell, but more like a swarming intelligent beehive the size of a solar system. Its primary purpose would be to orchestrate the Penrose process on an industrial scale. Automated mass drivers, perhaps using nearby asteroids or manufactured matter, would fire trillions of pellets into the ergosphere every second. Each pellet would split its negative energy core, feeding the black hole, its high-energy counterpart being caught by the sphere's collection arrays. The entire structure would function as a single integrated machine, a gravitational gyroscope converting the raw rotational energy of the black hole into usable power with breathtaking efficiency. But it wouldn't stop there. An advanced civilization would waste nothing. The sphere would also be designed to collect the faint, steady whisper of Hawking radiation, the slow quantum evaporation of the black hole itself. This is a trickle of energy compared to the Penrose torrent, but over cosmological timescales, it is a reliable and constant source. More importantly, the immense energy generated by the Penrose process would itself produce waste heat. A Dyson sphere would capture this thermal radiation, using it to power secondary systems to warm habitats, to create Earth-like biomes on a scale of millions of worlds orbiting in the structure's delicate framework. It presents a vision of a civilization that has transcended the need for planets, a society that lives in a self-constructed heaven powered by the most fearsome object in the cosmos. They would be true masters of their gravitational environment, their existence a testament to the ultimate potential of intelligence. They would not just be stealing energy from a black hole, they would be in a symbiotic relationship with it. By feeding it negative energy through the Penrose process, they would be slowly, infinitesimally spinning it down. Over countless eons, they would be taming the beast, gradually drinking its rotational energy, until it became a placid, non-spinning Schwarzschild black hole. In a very real sense, they would be consuming its power, extending the life of their civilization by calming the heart of the abyss. This is the ultimate cosmic inheritance, a bank account of energy so vast it could fuel a species' entire journey toward infinity. And this perhaps is the true climax of our story. It is not a sudden breakthrough, not a working prototype unveiled in a lab. It is the realization that the human mind, bound to a fragile planet, orbiting a humdrum star in a quiet corner of one galaxy, among trillions, is capable of conceiving of such a future. The Ergosphere has given us a new landscape to explore, not with rockets, but with reason. The mathematics are sound, the physics are confirmed, the simulations run without error. We have discovered a fundamental mechanism of the cosmos, a source of power that is not hypothetical, but is woven into the very fabric of space-time around every single spinning object in the universe. The question of can we steal energy from a black hole has transformed. It is no longer a simple yes or no. The answer is a narrative. It is the story of our own intellectual evolution. The Ergosphere stands as a silent promise, a cosmic beacon lit by the laws of physics, illuminating a possible future for intelligence in the universe. It tells us that the universe does not necessarily end in a slow, cold heat death. It tells us that for those who are clever enough and brave enough, there are reservoirs of energy that can stave off the darkness for timescales that render human history to a mere blink of an eye. We may never build these machines. Our civilization may falter long before we have the chance. But the fact that we can sit here today and understand how they would work, that is a triumph. It is a testament to the relentless, unyielding power of human curiosity. We have peered into the heart of the storm and seen not an engine of annihilation, but a fountain of creation. The grand cosmic engines we have imagined, the bombs and spheres, may be the destiny of a civilization far older and wiser than our own. But the physics that powers them is not confined to the distant future. The universe has had billions of years to experiment. The Ergosphere is not just a theoretical playground for human minds. It is an active, violent and spectacular force of nature that is shaping the cosmos right now all around us. The same mechanism that could one day power a Dyson sphere is already at work in the hearts of distant galaxies, creating phenomena so powerful they beg a belief. The universe, it turns out, has already built its own Penrose machines, and their fury is visible across the entire observable universe if you know where to look. And so we are left here at the edge of this gravitational vortex, faced with a challenge that seems to border on the divine. The staggering engineering required the materials yet to be conceived, the sheer audacity of planning a mission into a realm where space and time themselves have been bent to the breaking point. It all conspires to place this grand cosmic heist firmly in the realm of a distant, perhaps unattainable future. For our civilization at this moment in our cosmic infancy, the Ergosphere remains a fortress, its treasures locked away behind the most formidable defences the universe can muster. But to dismiss this entire quest as mere science fiction, to shelve it as a fanciful dream of future generations, would be to miss the most profound truth of our journey. It would be a failure to recognise that the true value of this exploration was never solely about building the machinery to tap this power. The real triumph, the enduring legacy of this magnificent idea, lies in what the very thought of it has forced us to become. It has been a catalyst, a theoretical crucible, that has forged our understanding of the cosmos into something new, something sharper, and something infinitely more wondrous. The question, can we steal energy from a black hole, has been a key that unlocked doors in our own minds, leading us into rooms of reality we never knew existed. Our story began not with telescopes or spacecraft, but with a whisper in the chalk dust on a blackboard, a ghost that haunted the elegant architecture of Einstein's equations. For decades after general relativity was born, we viewed the singularity as the universe's ultimate dead end, a point of infinite destruction, a one-way street from which nothing, not even information, could return. The black hole was a cosmic villain, a gluttonous monster, defined only by what it consumed, a symbol of absolute finality. It was a conception born of our deepest fears of annihilation, of oblivion, of an end with no possibility of renewal. The universe in this telling contained places of no escape, and that was a chilling, humbling, and seemingly complete thought. Yet within the beautiful, unforgiving logic of the mathematics, a paradox was stirring, an anomaly that refused to be silenced. The numbers hinted that the story was not so simple, that the monster possessed a secret, a hidden dynamism. It was the recognition of a spinning black hole, the Kerr solution, that first cracked open this monolithic view of cosmic nihilism. Suddenly, the black hole was not a static drain in the fabric of space-time. It was a gyroscope, a colossal flywheel, storing an amount of rotational energy so vast that it defies all terrestrial comparison. Imagine the combined energy output of every star in our galaxy collected and concentrated for millions of years, and you are only beginning to approach the scale of power held in the spin of a single supermassive black hole. And encircling this spinning titan was its enigmatic cloak, the Ergosphere. This was not a physical barrier, not a wall of matter or energy, but something far stranger, a region born of pure geometry. It was a domain where the very framework of reality is dragged along a whirlpool of space-time, where standing still is an impossibility. To an object entering this domain, the universe is no longer passive. Space itself has become a current, an inexorable river flowing faster than light, pulling everything with it around the central abyss. Initially, this was a mathematical quirk, a piece of theoretical landscape so alien that it seemed to have no purchase on the physical world. It was a phantom zone, a curious consequence of taking the equations to their most extreme and logical conclusions, a place for thought experiments. Then came the paradigm shift, the moment of intellectual alchemy, when Roger Penrose dared to treat this mathematical abstraction as a real place, a place with rules that could in theory be exploited. His thought experiment, the Penrose Process, was more than clever. It was revolutionary. It transformed the Ergosphere from a passive oddity into an active reservoir of near-limitless energy. The idea that you could enter this gravitational storm, sacrifice a part of yourself to the abyss, and emerge not weaker but stronger, supercharged with the black hole's own rotational fury, was a profound reframing of our relationship with the cosmos. It suggested that the universe's most destructive entities were also paradoxically its most generous fonts of power. The monster, it turned out, had a heart of pure energy, and there was a way, however theoretical, to receive a transfusion. This was the spark, a single luminous idea that illuminated the darkness surrounding the event horizon. It told us that the laws of thermodynamics, the sacred principles of energy conservation, still held, but in a way that was twisted and magnified by gravity's supreme power. The black hole was not a closed system, it was a participant. It could lose mass, it could slow its spin, it could in effect be mined. This conceptual breakthrough sent shockwaves through the world of physics, inspiring a generation to look at black holes not as endpoints, but as engines. And if they were engines, then where was the evidence of their work? Where was the exhaust, the cosmic signature of this incredible process playing out on a galactic scale? The quest moved from the theorist's mind to the astronomer's observatory. We began to scan the heavens not just for objects but for proof of a process, and the universe in its own time began to provide answers. It gave us the quasars, those terrifyingly bright beacons of cosmic dawn, blazing with the light of 1 trillion suns from the edge of the visible universe. What could possibly power such a celestial blowtorch? No star, no supernova, no known nuclear process could account for such a sustained and cataclysmic output of energy. The answer we slowly realized was hiding in the dark heart of these young galaxies. At their cores were the supermassive black holes, the very same spinning titans predicted by the mathematics, and they were not quiescent. They were feeding voraciously on surrounding gas and stars, and through a process far more efficient and violent than Penrose's simple projectile, they were converting the energy of their own spin into light and matter. The Blandford-Zinajek mechanism gave us the physics for this grand spectacle. It took the abstract notion of the ergosphere and wrapped it in the tangible chaos of magnetic fields and superheated plasma. It painted a picture of a cosmic dynamo where magnetic field lines tangled and twisted by the black hole's ferocious spin act, like colossal transmission lines, flinging matter outwards in jets that travel at nearly the speed of light. These jets, these magnificent pillars of creation born from destruction, became the smoking gun. They are the ergosphere made visible, the exhaust fumes of the universe's greatest engines, stretching for hundreds of thousands of light years across the intergalactic void. When you see an image of a galaxy like M87 with that ethereal luminous spear piercing through its core, you're no longer looking at a mere curiosity. You're witnessing the Penrose Process writ large. You're watching a black hole surrender its rotational energy to the cosmos, powering a celestial particle accelerator on a scale that dwarfs our most ambitious dreams. This journey from a subtle anomaly in an equation to the observed reality of a galactic jet represents one of the greatest triumphs of the scientific method. It is a testament to the power of pure thought to anticipate the workings of the universe. It required the solitary genius of theorists who could navigate the treacherous waters of curved space-time with only pen and paper. It demanded the patient dedication of observational astronomers building ever more powerful telescopes, peering deeper into the night sky and collecting faint whispers of light from billions of years ago. And it culminated in a global collaboration of unprecedented scale, the Event Horizon Telescope, which synchronized observatories across our planet to create a virtual lens the size of the Earth itself. When that first image of the shadow of a black hole was revealed, it was more than just a scientific milestone. It was a moment of profound human connection to the cosmos. For the first time, we were not just inferring or modelling, we were seeing the abyss. We were gazing directly at the precipice of reality, the boundary of known physics. And in the swirling asymmetric ring of light surrounding that darkness, we saw the tangible proof. We saw the Doppler-shifted glow of plasma being whipped around at relativistic speeds, a final confirmation that the space-time around this object was not static. It was in motion. The ergosphere was real. The great cosmic flywheel was turning right there before our eyes, 55 million light-years away. It was a vindication, a final breathtaking piece of evidence that solidified a century of daring theoretical exploration. The ergosphere now stands as a cornerstone of modern astrophysics, a critical component in our understanding of galaxy formation, of the distribution of heavy elements, and of the cosmic feedback loop that governs the life and death of stars on a galactic scale. It has shown us that the universe is not a quiet, empty place with isolated islands of activity. It is a dynamic, violent, and deeply interconnected system. The actions of a single spinning object at the heart of a galaxy can dictate the fate of billions of stars across tens of thousands of light years. The energy unleashed from the ergosphere can trigger bursts of star formation, or it can blast away the gas needed for new stars, effectively sterilizing an entire galaxy. The black hole, once the ultimate symbol of isolation, is now understood as a primary architect of cosmic structure. But the legacy of the ergosphere extends far beyond the realm of astrophysics. It has fundamentally altered our philosophy of science and exploration. It has taught us that the universe's most profound secrets are often hidden in its most extreme and counterintuitive environments. Our earthbound intuition, sculpted by the gentle gravity and placid space-time of our world, is a poor guide when we venture close to the event horizon. Here we must rely on the pure cold and often bizarre language of mathematics. The Ergosphere is a testament to the power of that language to describe realities that our minds can barely grasp, to predict phenomena so strange they feel like they belong in mythology. It forces us to be humble to accept that our common sense is a local ordinance, not a universal law. This quest has also redefined our concept of resources. For all of human history, we have harvested energy by burning fuels, by harnessing the flow of water, by capturing the light of our nearby star. These are all processes of transformation, of releasing potential energy stored in matter. The Ergosphere offers something completely different. It is a chance to harvest energy, not from matter, but from the geometry of space-time itself. It is the energy of motion, of pure angular momentum stored in the curvature of reality. The notion of harnessing this is so profound, so fundamental, that it feels like a step up to a new level of cosmic existence. It's the conceptual leap from a species that burns wood to one that understands immersive. And now we glimpse the next step, a species that might one day draw power directly from the spin of a gravitational singularity. This single focused question about black hole energy has pushed us to develop new mathematical tools, to invent new observational techniques, and to run computer simulations of unprecedented complexity. It has fueled decades of research into quantum field theory and curved spacetime, leading to other astonishing predictions like Hawking radiation, which showed us that not only can black holes give up their rotational energy, they can also over unimaginable timescales evaporate and die. The black hole, once an eternal prison, was revealed to be a finite object obeying even deeper laws of nature that we are only just beginning to uncover. It is a perfect example of how pursuing a seemingly narrow, impractical question can lead to a cascade of discoveries that enrich our entire understanding of the physical world. And so, we look to the future, to the unwritten chapters of this story. Perhaps one day our distant descendants will not see the Ergosphere as a theoretical curiosity or an observational target. Perhaps for them it will be a known territory, a resource, a workplace. They may command fleets of automated probes that dance at the edge of the abyss, executing the Penrose Process with an elegance and precision we cannot imagine. They may build Dyson spheres, or ring worlds not around stars, but around the spinning hearts of galaxies, tapping a reservoir of power that could sustain a civilization for eons. For them, the jets of M87 might not be a subject of astronomical wonder, but a beacon, a cosmic lighthouse powered by their own technology, a signpost in a galactic network of harnessed black holes. This vision may seem fantastical, but it is the logical endpoint of the path we're on. It is the ultimate expression of the human drive to understand, to explore, and to engineer our environment. We are a species that sees a waterfall and imagines a turbine. We see a bolt of lightning and imagine a power grid. And when we see a spinning abyss warping the fabric of reality, we cannot help but ask, can we use that? This question is not born of greed or arrogance, but of an insatiable, relentless curiosity that is our species' greatest gift. It is the same impulse that led our ancestors out of Africa, that propelled navigators across uncharted oceans, and that lifted us from the gravity of our world to the surface of another. The Ergosphere then is more than just a place. It is a symbol of the frontier. It is a monument to the universe's boundless capacity for surprise, a constant reminder that for all we have learned, we are still just scratching the surface of a reality far more complex and magnificent than we have ever conceived. It stands as a silent testament to the idea that in the cosmos, the most violent and destructive phenomena often conceal the most profound sources of creation and energy. The universe does not give up its secrets easily. It hides them in the darkest corners, in the most violent storms, behind veils of impossibility. Our journey to understand it is a story of stripping away those veils one by one, through courage, ingenuity, and a stubborn refusal to believe that the universe has any truly unknowable places. The quest to tap the energy of a black hole continues not just in the designs of hypothetical future spacecraft, but in the mind of every physicist who wrestles with the equations, every astronomer who gazes into the deep field, and every one of us who dares to look up at the night sky and wonder at the majestic, terrifying, and beautiful forces that have sculpted the cosmos we call home. The Ergosphere is waiting, a challenge, a promise, and a gateway to a future we can only begin to imagine.